So everyone, welcome. Thanks for joining, and thanks everyone for joining online. So I have the privilege of an honor of introducing Conrad. So Conrad's joining us from Penn. He's a professor at Penn. The Penn Integrates Knowledge Professor, which is a interdisciplinary professorship, and which is fitting, of course, because Conrad has had a very multidisciplinary career. He did his PhD in physics and then worked in neuroscience on causal theory, on deep learning, on neuroscience, and has had many different, a very diverse and I would say eclectic research program. And he's had many awards and many distinctions and many honors, and you can read about those online. The thing that I anchor on when I think about Conrad, and I'm super thrilled that he's here and came to the West Coast. But anyways, the thing that really stands out to me about Conrad has been his appreciation and joy, from what I can tell, in mentorship. And ever since I've known him, I've known him for over a decade now. And when I was a student, and as a PhD student, I would talk to some of his friends or some of my friends that were in his lab, and they talked about how great of a mentor he was. And that really stuck with me. I didn't hear that all that often. And I kept hearing that over the years, that his students, some of which have come here and give talks in our AST series, really speak so highly of him as a mentor. And I think Conrad really wanted to scale that sort of education, and for that reason has launched and founded massive online courses to reach many more people. That started with NeuroMatch, which you may have heard of, which is a fairly large, very international neuroscience training summer course, and now there's a deep learning one as well. And more recently, he founded a new community called the Community for Rigor, and that's about giving educational tools to scientists, and really sort of scaling this idea that Conrad has to value really impactful work, not work that is just going to scale our H indices or citation counts, but really the thing that we actually care about, in this case, doing high quality science. So Conrad has, and he got a non-trivial amount of money from the NIH to do this and build these educational materials. So Conrad's going to talk about causality today, and I think it's extremely relevant to a lot of our work, because of course we care about doing fairly large initiatives, and it's hard to measure the impact of what we're doing, whether it's through open science and the LLMs that folks are working on, or us over at AST doing environmental work where our goals are really broad, and it can be difficult to think about what are we really doing, and of course that's important for us, and we want to be doing work that actually is truly affecting the bottom line. So I'm thrilled to that Conrad's here. Please take it away, Conrad. Thank you so much for joining us.
Wonderful. Thanks so much for having me here. I think my real focus is just on kind of interesting new ways of thinking. And science has this way of people do these little publishable computer science conference papers, one after the other in Europe and Korea and all that. But in reality, these local things don't necessarily get into the big topics that are so interesting. And so what I always try to do is encourage my students to think far range about new topics. And so I want to share some ideas with you, and I'm delighted that I'm here. So let's talk about causality. Why should we care about causality? Because it's the only question that matters. What do we use data for? Make better decisions. What does it mean, make better decisions? Choose of the set of possible decisions that we could take, the ones that make our life and the world better. And so if people talk about understanding, they universally mean causal understanding, because that's the kind of understanding that allows us to succeed in the world. If people talk about simulating brains, they mean kind of causally simulating brains. It's not enough to play the movie, but you want the flow of information to be right. If people talk about fixing medicine, all of that is about causality. And of course, machine learning is also about causality. Like people are like, oh, but MNIST, why is MNIST like about causality? Well, MNIST is to be used to deliver like letters to the right place. So the machine learning, the supervised machine learning shows up as a small piece of a causal system that we're optimizing. So everything is about causality. And causality is really weird. Let me maybe highlight that. So in our mind, we all think about the world in terms of causal things. Now I'm giving a talk because Patrick invited me. But this is weird. If we look at physics, if we look all the way at the quantum end, there's no causality. Everything in a way exchanges particles with everything else. If we zoom all the way out, there's no meaningful causality. Like, yeah, every piece of matter kind of interacts with every other piece of matter. And yet, for us humans, causality is super important. And I think we need to understand why it is that causality is so important for us if we are to build systems that feel intelligent, and if we are to build systems that we can optimize for human beings. And I argue that causality is a very peculiar aspect of our specific niche, and namely that it this place in the world where we live, causality is super sparse. And what do I mean with it? There's one hunter with one hunted at a given point of time. Now, there's so many objects, but there's a very peculiar link between those two that is really important. Food, shelter, switches, not a light switch. I push that button, it gets dark here. We all agree on that. How come that I know that? Well, I know that we designed the world so that it has these sparse causal relationships. And why is that so useful? Now, like once we have sparse causal relationships, we can do a lot of reasoning about those. And human tools, like we make tools more and more sparse in their causal role. Like a rock, we can do all kinds of things with a rock. A screwdriver only works with screws. And progressively, we have more and more specialized things. That's the reason why we don't have like one thing on our phones, but we have 1,000 apps that are all like one specific causal thing that they do for us. And we design our causal world to be even more causal. Human society also causal structure. Like I have a small number of friends that I regularly talk with. If I have an idea, I get that idea from one person, not like diffusely from everyone. No, someone explained it to me. And a sparse world makes thinking easy. Because we can like plan and reason on small graphs. We can basically sub-select from the world of variables, a relatively small set of variables that are interconnected with one another, and we can do planning within those. And also, we are so strongly growing up in a world with sparse causal relationships that if we are in a part of the world where the causal relationships are not causal, we will mistakenly believe that they're causal. So the brain has 86 billion neurons. Each of them interacts with 10,000 other of them. And yet brain scientists love these models where like one brain area only connects with 3 other brain areas. And when you talk with medical scientists, they're like, oh yeah, that's why the patient has this disease. And in lots of cases, not like take heart disease, it's not in that sparse domain. So there's something about the human niche where like our thinking can be very sparse. And there's something that as soon as we leave our niche, where things go very, very wrong, where we wrongly believe the world is sparse causal in cases that they're not. And I think this is a peculiar aspect of human intelligence. And I believe that any truly intelligent systems that we build will ultimately contain that. And I'd love to, like, if we have time later, to have that discussion to which level you agree with that view. So where do humans know causality from? Well, most of the causality that we know is that someone tells me. Now, like light switches, there's the switch goes on, like maybe the IT person would tell me, something like that. And maybe that's why LLMs are like actually quite good at certain types of causal reasoning. So that's the first thing, and that's probably the majority. The second one is you tried some random stuff, reinforcement learning style. Now, that is very important in my body. You know, like no one explains to me how my body works with all the muscles, but I'm gonna kind of pull all of them and do things. And when we are kids, we go around and turn on and off switches, like try and understand kind of the world by basically kicking it and seeing what happens. Those are the two main things. And then there is like something that still occurs, which is I'm not figuring it out, but like I observe someone else do stuff. And by observing them, I figure out how causality works in the world. We call that quasi-experiments in large parts of that field. And then kind of comes almost nothing. And then like in the end, Julia-Paul type directed acyclical graphs kind of can explain any causal relationship. It's just, I cannot come up with a single good human example of humans actually doing it. So I think the majority we get out of those three. Now, trying random stuff, reinforcement learning, you've of course seen a lot of that. So much of my talk will be focusing on this part. How can you figure out how causality works by observing the world, and how can you ever be sure about it? Now, briefly, why do we want causal representations? Now, I already mentioned it when we talked about the niche, but it should allow us to generalize better because the future is different, but causal factors remain causal factors. Now, like physics doesn't change over time, but the distribution of covariates in the world does change over time. And the compositionality of objects, which is a form of causality, if you want, doesn't change, while maybe the relationship between things and people does change over time. So in any case, generalization should be better. Also, if we can get into this space where causal links are sparse, then our system becomes super compressible, because like we don't have all these like weak sideways causal interactions, because it's super compressible is another reason for why it will be generalizing well. We can learn faster, we can communicate better. Just to be clear, the only way I can ever explain something useful for you is by being in this sparse causal space where it can be like, look, this is why this is happening, why this makes this happen, why this makes this happen, and this is how the world works here. And so human language is ultimately about that. And I should also mention, for people who come maybe from only a computer science direction, there's ample evidence that even human babies kind of have built into the way they perceive the world a strong drive to interpret it in terms of causal, in terms of sparse causal interactions. And of course, it supports counterfactual reasoning, and it helps us to get towards the future. Now, causality, if you come from outside of that field, is a most bewildering field. So in that field, we have a group of people who basically nod to Julia-Paul and prove theorems about causality. Most of these theorems don't apply to the real world. Why not? Because things are always confounded. There exists a corner of machine learning that says they're about causality. They basically use ICAN versions of that and use nonlinearity in that process, non-Gaussian, nonlinear, independent components to get at how causal chains evolve within the system. There exists sociology, economics that look at quasi-experiments, and we'll be talking about quasi-experiments. There's medicine, basically go do an RCT or go home. There's epidemiology, which means just like run big linear regressions with lots of corrections. And there's neuroscience, where it's perfectly fine to just believe that all correlation is causation. And today I will talk about like rather vanilla causal inference of the quasi-experimental type mostly. Before going there, though, I want to give you some intuition. So I always knew that correlation isn't causation, like they teach you, and I kind of had that intuition. But whenever I thought about systems in my head, correlation and causation seemed to be mightily similar. And I had to like really construct weird systems to make correlation and causation not be similar. And that's a weird situation. Like, how is it that all the things that we can think in our head have correlation as causation, and all the things that like seem to be happening in medicine and like economics in those areas don't seem to be like correlation as causation? Well, let's build some intuition for that. Let's have the most simple dynamical system that we have here. Xt plus 1 is just a squashing nonlinearity to make things stable for sure of axt. So A is the matrix containing the actual causal interactions plus epsilon t. So there's like Gaussian noise on each of these variables independently. So axt is n-dimensional. A is the causal matrix. So we have independent noise adding to all dimensions. We initialize it to 0. We make it that the largest singular value of A is 0.99 because, like, hey, we want like that the system is stable. Okay, this is the easiest system. Now, what should we expect here? We should expect that the time delay 1 correlations should approximate causality. Now, like A is how xt is coupled into xt plus 1. So what should we expect here? Is correlation and causation similar? Well, let's just see. Now we like simulate it any number of times if you want. So, oh yeah, and I forgot also, I make a spot because like all the things that we humans think about, and arguably most things in the real world are spot matrices. Now, here we have a 6x6 matrix. Here we have the causal matrix. We can display it as a set of errors, which is popular in the networks field. And then we can look at what the delay 1 correlations are, and look, they're very, very similar. Okay, correlation is causation. Konrad finished his talk and probably can go home now.
Okay, sorry, I didn't understand this graph. Can you explain it?
Okay, color-coded here is, here we have the connectivity strength, that's the A matrix. And color-coded here we have the average scalar product of xt with xt plus 1, the outer product. No, so it means that when neuron 0 is active, then neuron 1 is often, or like I call those dimensions neurons because I often talk with neuroscientists. But if dimension 0 is active at one point of time, then dimension 2 is often active at the next point of time. And that's how to read that matrix. And those two are very similar to one another. Well, let's see if we take the same generative model, no changes, and we just make it big. Like 6 is the kind of stuff, like a handful of variables fits into Konrad's head, no problem. 100 variables, like, definitely doesn't fit into Konrad's brain because, like, well, how could I simulate all of that? No, so let's see. So here we have correlation as causation. Let's now look at the same thing on a 100 by 100 matrix. Now, the very same generative model, no changes here. Here you have the true connectivity matrix A. Here we have the time delay 1 estimated connectivity matrix. And these two seem to have preciously little to do with one another. No, they're like really different. No. So we have a small system and correlation is causation. We have a bigger system and they start being unrelated to one another. And of course we can then quantify that. On this axis, we have the dimensionality of our system. No, and like it's of the kind of dynamical system that really makes sense in the world. Like there's a time scale order 100. In reality, many time scales are longer, and like there's a natural unit for time, which is the time over which like the dynamics kind of meaningfully, where like random noise is at least forgotten meaningfully over that period of time. And what we find is that, so now here we just flatten the matrices, raw correlation between them. And if we have a small system, say n is 6, then correlation and causation are very similar. And as we make this system be big, they become very different from one another. Why is that? Because all the dimensions that you don't observe start confounding the dimensions that you're looking at. Now here we're looking at pairs. And all the other dimensions act as confounders for the dimensions that we have. So what that means is we're in this really dangerous space where the systems that we can simulate in our head, correlation is causation. Therefore, we convince ourselves that, yeah, correlation is kind of causation. And if you look across scientific disciplines, they almost all have this bias of believing that correlation is causation. And like, look at machine learning people. They fit like a big model where like they have like patience and what they do and so forth to the data. And they could build a great predictive model. And then they're like, okay, what if we compare the people who take the drug versus those that don't take the drug in our deep learning system or whatever, we have that. But that assumes that correlation is causation. And therefore like these systems really go wrong. So, and it turns out that we can mathematically understand how they go wrong. Let's say we have a variable y that is affected by a set of variables xi, like that. Those are the causal interactions that we observe. And then there's causal interactions z that we do not observe from variables that we simply don't know about. And then there's noise. And now if you look at that, you can say that you get that the estimator that you get for the causal effect. Now, and this is in the linear regression domain. If you're in the nonlinear domain, things only get worse. But what you have is you first have the true value, and then you have a bias. That bias doesn't go away with more data. There's no way of making that bias go away. And that bias has the same form as the regressor for the original piece, which means that that bias, if there's many variables that you don't know about and few variables that you do know, then that bias gets to be very big. So where would that matter? Pretty much anywhere. Now, like we as humans always know only this tiny bit. No, like I have a patient. I don't know all the things happening in their blood and all the diagnosis of their parents and all the DNA that they have. Like I can never have all those things. I don't know their lifestyle, don't know their character. And because of that, we are always in that heavily confounded regime. And therefore, usually correlation is really far away from causation. Now, let's go into how the causality field, how the causal inference field deals with it. Now, here is why RCTs get us at the right variable. I have a variable X that I'm interested in. I have a variable Y that I'm measuring. And if I have confounding, I have a variable that affects those two, a variable that makes me be treated. Now take a case where confounding, and not all of causal inference is the field of dealing with confounding. Now, like typical confounding case, you look at people who take vitamin D, you see what the probability is that they're going to survive for a while. And you find that people who take vitamin D often survive for a long time. And guess what? Which people take vitamin D, which people live a long time, and therefore, like, it looks as if vitamin D really makes you immortal, or like at least mostly, where in reality, this is just a confounder. But if you're in the case of an RCT, you know, like you randomize the treatment, you throw a die if they're treated or not. Therefore, the confounder doesn't affect this. And therefore, anything that the confounder does to the outcome variable will, on the long run, average out. And therefore, you get an unbiased estimate of the causal effect of X of Y if you randomize like that. Now, here are the prompts for it. The first thing is if you have a confounder that affects those two, it will look as if they interact with one another, even if they're not. You will interpret it as causal when you're not. And of course, we're all machine learners here. Like, so what were we going to say? We will say, well, like, look, like, let's just get enough data. Like, we're Google. We get like all the data that exists on you. So therefore, doesn't the confounder go away? No, we could correct for that. We could use that to regress it out, remove the effects of it. Well, it turns out that there's also collider. So a collider is a variable that is affected both by X and by Y. If you correct for a confounder in a linear regression, in any kind of a regression system, you get better. If you correct for a collider, you get worse. So if X and Y have nothing to do with one another, and you believe that the collider is a confounder, you correct for it, all of a sudden X and Y start being related to one another. Now here's the big problem. Imagine I give you like all the data in a health record, or all the data in like some ecosystem, or all the data among some group of like interacting friends. The variables that I have, I can never know which is which. And like take the health system. I have socioeconomic status affects if I will take the drug, if I will take vitamin, and it will take how long I live. But at the same time, how healthy I am changes like which jobs I apply to. And therefore, how healthy I am ultimately affects the same variables, which is my socioeconomic status. And so in the cloud of variables that surround people, the things that you're interested in, X and Y, affect kind of that whole cloud, like that whole behavior. You know that you're sick, of course, you'll try and like get health insurance as quickly as possible, which means that health insurance now is like, it's clearly a confounder. Like health insurance changes how you're treated, and health insurance changes how long you live. But also, how healthy you are affects if you're going to get the health insurance. And ultimately, if you're kind of on the way out, affects the way you have health insurance. So colliders and confounders, the existence of them and the fact that you can never know which is which, and that the fact that everything is always mixed, makes the let's just throw machine learning at the problem be a strategy that can never work. So if we want to learn about causality, we need to think much harder than just like building big models that correct for the various confounders. And I want to tell you how we can do that. So here's an instrumental variable. So basically, Julia Paul says, well, give me a system like that, and I'm going to tell you if it can be identified. What the economists say, like, of all the systems that could be identifiable, we've only ever seen 3 of them that work for that. And one of them is an instrumental variable. What is an instrumental variable? I have a so-called instrument. That instrument affects the treatment, and for some reason, we know that it doesn't affect anything else apart from through the treatment. Now that is the assumption of that. For example, you could say an instrument might be, am I born at the end of December of one year or early in January of the next year? It makes a big difference, and it's arguably it only has an effect over the birth year that you have. And or alternatively, you get randomly assigned a doctor. So there's nothing that affects the doctor that you have, and maybe that doctor only really has an influence on one small part of your treatment, and the doctor is like the random variable. So the reason how we can use that to figure out causality is there's basically this piece of the world that we see that does things, and we understand it, and it only. And because we understand it, we can then use that as a mechanism to figure out something. Now, like if I see you use the light switch, I can say, well, like at that specific point of time, you're doing it, I'm not doing it, I'm not randomizing it, but like you're effectively a randomizer, and the only thing that you do at that point of time is flip the switch. And so briefly, if the so-called and the key assumption here is the exclusion restriction, that that instrument only affects anything else in the world through the treatment, and it doesn't affect it with confounders. It is not affected by confounders, and it doesn't directly affect the outcome. And this is something in econ that you can often reasonably assert by understanding the problem domain. Yes.
In the previous example of health and lifespan, what would be an instrument?
Of health and lifespan. Like, let's take the example of vitamin D. Imagine we take people who only come in for vitamin treatment that have been randomly assigned a doctor, and half of the doctors really like prescribing vitamin D, and half of the doctors really hate prescribing that. Or alternatively, you live in a rural area. So economists often think about taxes there. Like you live in a rural area, you're on one side of the county line, and the county increases its taxes relative to the other county. Now you can say it's kind of random which side of like the county line you live, like you just live in some rural area. If you find yourself lying on one side versus the other one, the only difference at some level is that randomly you get switched in tax rate. And out of that, you can then figure out how tax rates, say, affects like how hard you work or what you're doing, or like how likely you're to go to university. And there's a lot of versions of that.
So another question
Yeah.
related to this is the instruments sort of just a way to induce a randomized treatment?
So the interesting thing is it's not really a randomized treatment, no, like it's that someone else randomizes for you. No? Like a randomized treatment is if you throw the die. In this case, you can say indeed an instrument is just the world kind of throws the die for you. And then there's of course versions of that where you observe that die. There's versions where you don't quite observe the die. There's versions where you only see what the treatment is. There's version where the die has lots of values that are uninterpretable, and only some versions where the die is interpretable. But yes, exactly. It is in the case where not you randomize things, but where the world randomizes for you.
Yeah, I'm thinking of like a medical trial with a placebo versus a real medicine. You don't know what it is, somebody chose it, and now you can.
Yeah, so it's more the case, no, if you run the RCT yourself, you're in an RCT situation, you don't need to think about about instrumental variables. But let's take a pre-planned RDD where you're like, I get enough money to treat 1,000 people. I'm going to treat the 1,000 people that I think need the treatment at most. And now I consider compare the 900 ranked to 1,000 people with the 1,000 to 1,100 ranked people to kind of see what happens at that place, where you effectively have an instrument that is random, that only affects them through the treatment, that's effectively random, and the method is called regression discontinuity design in econ. And in that case, so in a world where you have discontinuities, they effectively produce instruments for you. So anything that has an instrument that you observe, anything that has a threshold where you observe what goes into the threshold, you can construct an instrument out of it that is, if you understand the domain well enough, good. And you see one thing here in the way I talk about it, as opposed to general purpose machine learning, you need to understand the domain to be able to do causal inference. So before I understand things, I can't do anything. I need to understand that in this specific system, doctors are assigned randomly, and in this other system, they're not. And I need to know, like, here's the threshold, and people get to cheat to iterate until they're above the threshold. Whereas here's another system with a threshold where people only have one shot, and then we take the first reading that we have. So it requires domain expertise, but once you have that, you can then use the tools of machine learning. And I see I'm like super slow, so let me try accelerate a little bit. If the assumptions are correct, what you do get is you get the quasi-experimental design gives you an unbiased estimator with larger variance than if you have another estimator, and you're biased if you do regular regression. But of course, if your assumption is wrong, you actually introduce a very strong bias, and you also have like worse variance. So it only works if you really understand the problem domain sufficiently well. And I should say, for people who want to like play with these things, we have a nice set of tutorials that people can use there. There's also a review paper. Okay, let's look at about a concrete case where machine learning can be used from that domain. Like there's two directions we can start thinking. How can these quasi-experimental things be built into machine learning algorithms? And we can ask, how can machine learning algorithms be built into these algorithms that people in econ and newly neuroscience and medicine like actually use. So we're interested in some treatment, maybe a treatment, do I feed the geese grain? And some outcome, how many eggs do they lay? And you can say there's confounders, maybe how heavy the goose is. And there's still a problem, which is non-compliance. Like you might have like geese that say just like, I don't take grain, whatever. And you might have always take this. I only eat grain, like feed me whatever you want, but I'll only eat that. And then there's like the actual compliers. And if you have these non-compliers, you lose statistical power. On this axis, you have estimated power. On this axis, the number of units that you exclude. And in that specific case, we have 4 non-compliers, and all the others are compliers. If we can use machine learning to find out which units we should throw away, we get better statistical power. That matters because the variance of our IB estimator goes as 1 over p comply squared. And basically, if we're in the typical situation where there's a lot of non-compliance, if you ever work with medical data, it's horrendous non-compliance. But even if you work on, let's say, decision support systems of any kind, humans are not very good at complying with what your algorithms tell them they need to do. So in that case, it helps to exclude. And now then the effective n is n times p comply. P comply in medicine is often 1/10. So being able to get rid of those is really very helpful. And now can we do data-driven exclusion criteria? So what's the idea? I look at all kinds of samples in my data set, and I figure out for which data sets do we believe people will do, for which variable points do we believe that like we actually have like this randomization, this thresholding, whatever it is, and in which cases will people be non-compliant with things, and then we throw away all the things that are non-compliant. And we could like use like feathers and feet, and I think it's fun how my student like used that example. But like what we have here, data-driven exclusion, you can see the estimated power as a function of the proportion of compliers really helps a lot throughout that overall range. Now we'll do that on some real data, insurance data from Optum, regression discontinuity design. If your A1C is 6.5 or higher, you should be called a diabetic, and guess what? Doctors are totally non-compliant with those kinds of medical guidelines. But then if you're diagnosed as a diabetic, your A1C should get better, which just means like you have less sugar in your blood. And here we have the standard analysis where we have the discontinuity. If we do data-driven exclusion, we get that the effect is bigger, and the follow-up A1C, we also get a better, more fine-grained estimate about it. So there's something weird about it from the logic. You know, like what we usually do in medicine, we're like, let's estimate that variable. What we now do is we have two machine learning pieces. We have a fast machine learning piece, which so they say like, yeah, you're the kind of compliers, you're the kind of non-compliers, and therefore I will ignore these guys and just fit for you, which means that ultimately you can only make statements about those people that the oracle says are in it. But about those people, you can perfectly make statements. And our predictions only apply to those. And over the others, we can't know anything. Like it could be that the people who are non-compliers also are guaranteed to die for some reason, or they're guaranteed to get bad treatment. So like the doctors just will treat them badly at a later point of time. Any of those. And we're currently working on using similar methods to basically mine through data sets of millions and millions of US patients to find all the opportunities where we can use that to make medical statements. Cool, so now I get to tell you about the second. Yes.
Is there a risk that the non-compliance that you're removing are correlated with one of the variables, and so your findings are actually
Yeah, not only is there a risk, they're guaranteed to be correlated with it. Now, that's what the machine learning system does. It looks at correlations with variables and just says, you know, people with a rural doctor, they do all kinds of things. Now, like, this is the kind of implicit logic that's there. So, but that isn't really a problem for us, because what I want to know is I want to be able to make causal statement. This patient would benefit from that. Now, it means that the non-compliers, I don't know if they benefit from a treatment, but it means I can now say confidently for the compliers, this treatment's great for them. And I know for a new patient, is this the kind of complier or is this the kind of non-complier? And so basically it produces a situation where for the compliers, you can make confident statements. And for the non-compliers, the question is how you should think about it. Maybe they're the same in a way, then they should get the same treatment. Maybe they're very different. And where you are totally depends. Like if you're in like a social decision-making situation, trying to like, model a network of scientists, then this might be a very, very bad model that they're the same. The compliers might act very differently. And in other areas, like when it's physics, more or less, you expect them to be the same, they just have different preferences. Now I will talk about something completely different. I told you so far about quasi-experiments. Let's talk about the extreme other end of things, which is, we all know the bitter lesson. Now Rich Sutton observes that we are that machine learners build in all this brilliance into their algorithms, and they solve real world problems, and then more data and more compute comes around, and general purpose compute always wins. And therefore anything that us applied machine learning people do is ultimately futile. And arguably that same phenomenon is going to come for causal inference, and I think relatively quickly. That's from a little paper that we call, that was originally called meta-learning causality.
Do you think it will come? Because I said before,
Oh, yeah,
You know,
so
with causal inference, like there's always confounders, and then if you don't know, then like, what would it help to use more data or more computation?
I always disagree with myself. I think that quasi experiments are, as long as we have causal inference in the small data domain, is very strong. And now we'll go into the more big data domain. But look, there's domains where you can't avoid it. You know, like where you have like in medicine, lots of diseases have like ultimately small groups. You can't like really meta-learn much there. And I think that the same is true for a lot of data sets that basically where we have a fractal kind of like variance that's being added. In that case, you can never be like the bitter lesson can never come, because within like each small bracket you will always have a relatively finite amount. But yes, I mean, like, yes, I do. The irony isn't lost on me that like the second part of the talk does kind of argue that the first part of my talk is unnecessary, but bear with me. So supervised learning, like we all know the setting, we have like the X and we have the Y, and we get good at mapping the X to the Y. And now, if you look at causal inference, it looks very different. Like as you saw in the early paragraphs, the field of causal inference, or in the early slides, the field of causal inference is full of like big thinkers that have like really big ideas about like how we could figure out causality in the world. So what we have is we have human knowledge that ultimately gets built into a handcrafted algorithm, and then we run the algorithm together with some data which tells us about causality. And let's see, is that the only way how we could do it? No, we could, like, of course, do meta-learning of this, where you could say, I don't have one causal inference problem, but I have lots of them. Maybe I have 1 million drugs that I tested at some point of time. Maybe I have like a large number of causal inference problems in some domain that are in a way very similar to one another. In which case I could say I take all the causal inference problem, the things that I learn about is ultimately the algorithm, and then I bring the algorithm together with new data and estimate causality. Now that is like exactly the bitter lesson applied to causal inference. Instead of like doing causal inference by domain knowledge, we like use a meta domain where you have lots of samples of domains out of like some universe of domains. And we see how good those algorithms are. And the problem here is I needed a data set with lots of similar causal inference problems. And people run randomized controlled trials. They run A/B tests in companies. I wasn't able to find any like really great real world data set that kind of has a lot of similar causal inference problems. If I was a big company, a tech company like Google or something, I could get lots of app placement things and see if I can do meta learning there. But what I did here is I took a system because I had it. This is the 6502. It's the classical microprocessors. People of my age learn programming on that thing. And the great thing is we know causality, or it's easy to define causality. We have the full net list of that thing and we can simulate it. But at the same time, it's kind of non-trivial data where the system has like clocks and does things. And the data that we use is from the game Pitfall. So it's like a remarkable level of like complexity. Now, what's the causal inference problem here? I give you a pair of transistors. And I'm just asking you, does the first transistor causally influence the other transistor? The great thing is there's thousands of them on the microprocessor, and like lots of them. And there's causal player pairs here. Here we have a non-causal pair. In both cases, we basically get, as a function of time, the voltage that each of the transistors have. And then the question is, can I give you two voltage traces of two transistors, and can you just look at it and tell me which of them causes which other? And we use the standard perturbative definition of causality. We basically take the transistor, we simulate like Pitfall, and then we inject current into a transistor. We simulate Pitfall again, and we see what the difference is. Here, what happens if you take out one transistor, another transistor, and another transistor. So some of them are connected to lots of them, some of them are connected to very few of them. And then we do an honest validation of that. We have like two non-overlapping things where no transistor is used in both of them. And we basically train on one of them and we test on the other one. And the great thing is we still have thousands of the comparisons in each of the buckets. So we have enough data to do the meta-learning. And then guess what? We're doing like a standard transformer architecture because we're not that creative. Standard window embedding layer, sequence encoder, global pooling head, and giving us a standard system. Okay, here we have how good we are at predicting on average the transistors on the test set. Correlation is something that people sometimes use in those domains as bad as chance. But hey, people do much better, and like mutual information, like really like meaningful. Yeah, it does better than chance. And Granger causality does even better than chance. But guess what? Like if we meta-learn things, we're doing much better. Now you can say, well, but like, look, Granger causality 0.7, it's not like all that bad. Neuroscientists like using Granger causality. Well, what if we add a little bit of noise? Well, all of a sudden they're all chance, and LSTM transformer models kind of still do very well. Why? Because like given enough compute and given enough data, you're always better. And then does it generalizes? Yes, we train on Space Invaders and then see how well it does on Pitfall and Donkey Kong. And like, yes, they generalize well, as they arguably should. They focus on the things that matter and are like, how can I causally figure out that one transistor affects the other one? I want to look at the place where it switches, and I want to like see, does it have a voltage influence on the other? And it seems to be doing it. Okay, so, and this is a totally general purpose strategy for any kind of causal inference problem. If you give me enough of those causal inference problems from the same domain, I can learn an optimal algorithm from that space. So what are the, yes?
Trying to wrap my head around this. So you have lots of data of pairs of transistors that either are causally related or not.
Yes.
And as we're looking at that time series data,
Yes.
you're a transformer, you're trying to predict.
Yeah, we're basically training a transformer so that the transformer gets to be a causality detector.
And this is causality as opposed to correlation because of the time axis.
It is because the ground truth data that we give to the machine learning system comes from perturbation experiments.
And you
No,
put
so-
it in the input, or is it something that you try to predict during training?
During training, we're not predicting it. During training, that's our ground truth data.
Yeah, but is this part of the loss that you're trying to predict the causal
The-
relationship, or
yeah.
is it part of the input?
That's part of the loss.
Okay.
The loss says, be good at telling me based on the two temporal traces if it's causal or not. It's
So
like,
what in the figure you have like these two inputs, right? Both the data and the causal relationship.
yes.
So because it's just like to getting the data for the
Yeah,
you
you use ground truth data from perturbation experiments, which is arguably causal ground truth. And you just use that as target for supervised machine learning. No, it's really the perfect standard setting. And can you use tricks to make it more data efficient? Sure. If you give me like a data domain, I can say, well, okay, let's use an LLM to like narrow down which paths are realistic. And so one can like soup up that idea in lots of ways. But the important thing is we're kind of like reformulating the problem from a causal inference problem based on human knowledge to one based on meta-learning. And in a way, it's the same thing. Now, I told you that we know in causal inference, we always need to build in causal knowledge to get a system that can tell us about causal inference. Only in this case, we don't build it in through generic statements. A and B are conditionally dependent on C, as we do in causal inference, but rather like, this is the correct causal answer for this problem. This is the correct answer for that problem, and so on and so forth. No, it's just like converting it into a supervised learning problem.
And what are the features that you use?
The features, we like literally just tokenize the voltage over time and put it into a standard transformer. Great. Okay, pros, you need lots of data. No, cons, you need lots of data. It's totally impossible for a human to understand how it works. You know, like, and yes, I know lots of people are working on interpretable AI, but I don't think that that's possible. And we'll see. And of course, it's also biased. You know, like the system will kind of know, oh yeah, if the transistors are mostly quiet, then it's like kind of less likely that they're connected. So it will use all the information that it has. The pros is if you have enough ground truth, it's guaranteed to beat any system any algorithm you could think of. And you have meaningful proofs. Like you can say, in the same way as in empirical risk minimization, we get proofs through performance on a randomly sampled subset of the data. Here you get proofs through a randomly sampled subset of causal inference problems, but it inherits exactly the logic of supervised learning. And I think it's a new approach to get into a messy observational spaces. And back to how we do things relative to AI systems, I think LLMs can capture parts of causality within text. Reinforcement learning system can figure out causality, but without explicitly representing them as a causal system, it's hard for them to meaningfully reason with it. And quasi-experimental data is arguably a complete blind spot in machine learning. I know the world has very, very few people who ever did a quasi-experiment and also machine learning at the same time.
Just one clarification on the first point you can answer. Are you saying that things that are written causally, like, friction causes things to slow down? So
Yeah. Yeah, look, I told you that most of the causal knowledge that people have in the beginning, they have from being told about it. And in the same way, like, yes, an LLM like reads somewhere like stuff that moves fast has friction over the surface over which it's gliding. And out of that comes then the causal chain of like the surface property affects the speed and the deceleration of the object that is sliding on it. So yeah, so it's exactly equivalent to the first mode. Now, like here I'm making the point that like the three modes of how people learn, which is someone tells you, you figure it out, or like someone else does stuff and you figure it out based on that they want, that they do. We can rescue those three things into like the land of machine learning.
Your previous experiment was about, you have this other mode also that people take lots of data and somebody labels them, then you can also clean it if you have enough labels.
Yeah,
Causality labels. Huh?
Yeah, you can say, like life of a kid has a lot of ground truth causality, where like maybe you try something and mom is like, if you hadn't pushed that, it wouldn't have the water, wouldn't have come out of it. And so in that sense, you can say maybe the way people actually deal with causality is of the nature of what I was talking about in the second half of my talk, namely you learn it by basically getting causal ground truth on a lot of data points. No, and that's like if you see like little kids, they go around and like kick things, move things, push things, and arguably that's exactly the kind of data you'd want to do ground truth driven causal inference. And in fact, if you talk with people, unless they're trained as a professional statistician, the way people think about causality is absolutely bizarre. It's not that they're like using directed acyclical graphs. They're mostly like, yeah, like whenever I see this thing, it's kind of like that's how it works, and with a lot of like unjustified assumptions. Okay, take home message. This is the last slide. I'm sorry that I'm already at minute 55. Causality and machine learning have overlapping problems. There's so much to learn from the many communities that deal with it, and I think there's so little overlap between causality and machine learning that there's a really big opportunity. I should mention in this context the CLEAR conference, where a lot of the discussions are happening now. And what I showed you concretely is exclusion can be a meaningful data problem, and maybe we should look for ways to learn how to do causal inference from large data sets. With that, thanks so much for having me here.
Thank you. So we can take questions. If folks online, feel free to jump in, or if there's more questions here, just unmute yourself and feel free to jump in. We should probably, I guess I can hit unrecord at a certain point. That's fine. Any questions here?
One thing you mentioned is causal inference is not linked a lot in ML. Is that the reverse side of it, where LLMs are being used for causal inference, or?
So there's this couple of recent studies where people ask, if you ask an LLM about a causal relationship, how good are they at that? The big problem is because the deep down an LLM is a lookup table. So LLMs won't figure out how causality works. They will make statements about causality that human beings might be highly probable to make. And that, of course, unfortunately leads into a situation where you cannot use LLMs to like produce better or newer, like, or more meaningful causal inferences. But it is a way of basically extracting what humans by default know about causality and using it for something. And that's useful because if you have some causal knowledge, you can always use the existing causal knowledge to better learn about other causal knowledge. So in that sense, extracting from human language causal knowledge promises to kind of open up causal inference.
You tried kind of a similar thing with like, or do you know of anyone who's tried a similar thing as like trying to predict, you have like pairs of causal relationships that you know, and instead of like, and then predicting whether it was causal or not for like pairs of languages as a way of maybe like fine tuning a model, because the language model, it's not trained in a way to directly do causality, but maybe once you have the base weights, there might be a way to fine tune the model so that you have tons of pairs of examples of causality. Like maybe you get it from like math or coding or something like that. And from that improve I'd be curious if that would improve how it's understanding of how causal relationships work.
I really like that idea. I'm not aware of someone who did it. Personally, I'm very much interested in science of science, like figure out how academia and science work as a system. And I do think that in domains like that, you could maybe really build these hybrid systems where you have some knowledge, like there exists some random experiments. Wonderful example. There's a wonderful Lafgren paper that looks at people who just NIH uses often scores to decide who gets a grant. And if you compare the people who are just below the threshold versus just above the threshold, you get like a good causal estimate. It's an instrumental variable study. And yeah, like, and you could maybe like get into that space where you have like some causal knowledge based on like what people say in language and some knowledge from other sources, and then maybe ways of combining them. I like that idea a lot. It's very cool.
I have one more question. I know folks probably have to drop or leave, but the question is, so back when I took a causal inference class back at CMU, and all those professors were obsessed with DAGs, and basically
it's world central for that way of thinking,
right? And yeah, for sure. And the case study that we spent a lot of time on, which I know is HR, hormone replacement therapy in postmenopausal women, and how that would like the disaster basically that was the observational studies attempting to infer causality from HRT from all the medical data, and ultimately it led to some pretty bad outcomes. Question is, and so we did like the whole reverse engineering thing, and lo and behold, if you apply this these very specific DAGs and like really do the best job at DAGs, then you wouldn't have come to this conclusion, blah blah blah. So I think the question I have is for you is basically like, have you done those kinds of retroactive? Is there not enough data there to do the kind of analysis that you could do, or like does it apply to these, like some of these horrible cases that we've looked at with the conventional way of thinking? Or is there not enough data there?
Yeah, so the first half of the talk basically boils down to you come up with the same answers as the CMU folks. Like it's that's very much like what they implicitly have is a quasi experiments where you can say arguably. Now they also have the faithfulness approach towards causality. So, but the second half of it, though, we can't currently do, but the right actor could and should do that. So here's what I mean with it. The world has literally 1 million RCTs. If I had the pockets of a big institute, I would probably try and get hold of all the data and then do what I did in the second half of the talk, only on like real world clinical data, and from that learn how to correct how things. Now, for example, take socioeconomic status. There's probably going to be something universal about like anyone who's high socioeconomic status has a certain way of like delaying their death on average. And you could generically correct for that. And like an algorithm that's meta-learned would basically learn the right way of correcting for like all those confounding variables. And yeah, but I don't have the resources of like a big institute, so not gonna happen right now.
Yeah, well, okay, thank you so much. Thanks, Conrad. Thanks everyone online, and yeah, thank you.
Thanks for having me.
Okay, cool.